The home inspector's findings suggest multiple grounding points exist in the electrical system. These include multiple water pipe grounds at the water heaters and a ground rod at the main service entrance. This configuration can create a potential for step potential, which refers to the difference in electrical potential between 2 points in the vicinity of an electrical grounding system. If someone is standing on the ground near a faulty grounding system, they could experience an electrical shock by simply taking a step. Several possible causes could contribute to this issue. Firstly, incorrect wiring practices may be present. Secondly, corrosion or damage to grounding wires could be a factor. Thirdly, the grounding system might be improperly installed or maintained. The consequences of step potential can be severe. It poses a serious safety hazard, especially in wet or damp conditions. It can cause electric shocks, burns, and even death. It is crucial to take recommended actions to address this issue. Contact a licensed electrician to evaluate the electrical grounding system and determine if any repairs or modifications are necessary. The electrician should take several steps. 1. Verify the proper sizing and installation of the ground rod. 2. Inspect all grounding wires for continuity and damage. 3. Ensure that the water pipe grounds are connected to the electrical system correctly. 4. Establish a clear path for electrical current to flow from the equipment to the grounding system. 5. Install ground fault circuit interrupters, GFCIs, to provide additional protection against electrical shocks. There are additional considerations to keep in mind. The presence of gas water heaters does not necessarily mean that the grounding system is inadequate. However, it is essential to ensure that all grounding connections are properly made and maintained. The ground from the water pipe should be connected to the cold water side, as this is typically the metal pipe that extends into the house from the main water supply. It is important to note that step potential can occur near any electrical grounding system, not just those associated with water heaters. To elaborate on grounding systems, let's delve deeper into the specific components and their functions. The ground rod, typically made of copper or copper-clad steel, is driven into the earth to provide a direct connection to ground. Its primary purpose is to dissipate electrical fault currents safely into the earth, preventing them from causing harm to people or equipment. The proper sizing of the ground rod is crucial for its effectiveness. The size depends on factors such as the soil resistivity and the required fault current carrying capacity. Electrical codes, such as the National Electrical Code, NEC, specify the minimum size requirements for ground rods based on these factors. The installation of the ground rod also plays a vital role. It should be driven deep enough into the earth to ensure good contact with the soil and to reach a stable ground potential. The connection between the grounding wire and the ground rod must be secure and corrosion resistant to maintain a reliable electrical path. Grounding wires, typically made of copper, connect various electrical components and equipment to the grounding system. These wires provide a low impedance path for fault currents to flow back to the source, allowing the circuit breaker or fuse to trip and interrupt the current flow. The proper sizing of grounding wires is essential to handle the expected fault currents without overheating or melting. The NEC provides tables that specify the minimum size of grounding wires based on the size of the circuit conductors. The routing and installation of grounding wires are also important. They should be installed in a manner that minimizes inductance and impedance, ensuring a fast and effective path for fault currents. Sharp bends and long runs should be avoided, as they can increase impedance and reduce the effectiveness of the grounding system. Water pipe grounds, as mentioned earlier, are another important part of the grounding system. They provide a connection to the metal water piping system, which is typically grounded to the earth. This helps to equalize the potential between the electrical system and the water piping system, reducing the risk of electric shock. The connection to the water pipe should be made on the cold water side, as this is the side that is typically connected to the main water supply and is in contact with the earth. The connection should be made with a listed clamp or fitting that is designed for grounding purposes. It is important to note that the water pipe ground should not be the sole grounding electrode for the electrical system. It should be supplemented by other grounding electrodes, such as a ground rod or a concrete encased electrode, to ensure a reliable and effective grounding system. Ground fault circuit interrupters, GFCIs, are an important safety device that provides additional protection against electric shock. They work by monitoring the current flowing in the circuit and detecting any imbalance between the hot and neutral conductors. If an imbalance is detected, indicating that current is leaking to ground, the GFCI will quickly trip the circuit, cutting off the power and preventing an electric shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. They can be installed in the circuit breaker panel or as receptacle outlets. It is important to test GFCIs regularly to ensure that they are functioning properly. The NEC provides specific requirements for the testing and maintenance of GFCIs. In addition to these specific components, there are also general principles that apply to all grounding systems. One important principle is that the grounding system should be continuous and permanent. All grounding connections should be securely made and protected from corrosion to ensure a reliable electrical path. Another important principle is that the grounding system should be properly sized to handle the expected fault currents. The size of the grounding conductors and electrodes should be based on the size of the circuit conductors and the available fault current. The NEC provides tables and guidelines for determining the proper size of grounding component. Regular inspection and maintenance are also essential for ensuring the effectiveness of the grounding system. Grounding connections should be inspected periodically for corrosion or damage, and any necessary repairs should be made promptly. The ground rod should be tested periodically to ensure that it is providing a low impedance path to ground. The NEC provides guidelines for the testing and maintenance of grounding systems. Understanding step potential requires knowledge of Ohm's law. Ohm's law states that the voltage, in volts, across a conductor is directly proportional to the current, in amps, flowing through it and the resistance, in ohms, of the conductor. Mathematically, this is expressed as voltage equals current times resistance, or volts equals amps times ohms. In the context of step potential, the voltage is the difference in electrical potential between 2 points and the ground, the current is the leakage current flowing through the ground, and the resistance is the resistance of the soil between those 2 points. The higher the voltage difference, the higher the leakage current, and the lower the soil resistance, the greater the risk of electric shock. Soil resistivity is a measure of how well soil conducts electricity. It is an important factor in determining the effectiveness of a grounding system. Soil with low resistivity is a good conductor of electricity, while soil with high resistivity is a poor conductor. The resistivity of soil can vary depending on factors such as moisture content, temperature, and the presence of minerals. Soil with high moisture content tends to have lower resistivity, as water is a good conductor of electricity. Soil with high mineral content, such as clay, also tends to have lower resistivity. The NEC provides guidelines for measuring soil resistivity and using this information to design grounding systems. Step potential is a phenomenon that can occur near any electrical grounding system, not just those associated with water heaters. It is important to be aware of the risk of step potential and to take precautions to avoid it. Some precautions that can be taken include avoiding standing near grounding electrodes during electrical storms, wearing rubber-soled shoes to insulate yourself from the ground, and contacting a qualified electrician if you suspect that there is a problem with the grounding system. The NEC provides specific requirements for grounding and bonding in various types of electrical systems. These requirements are designed to ensure the safety of people and property by providing a low impedance path for fault currents to flow back to the source. Grounding and bonding are essential for preventing electric shock, fire, and other electrical hazards. To further understand the requirements, it is important to understand the difference between grounding and bonding. Grounding refers to the connection of an electrical system or equipment to the earth. Bonding refers to the connection of different metal parts of an electrical system or equipment together to create a continuous electrical path. Both grounding and bonding are necessary for a safe and effective electrical system. Grounding provides a path for fault currents to flow back to the source, allowing the circuit breaker or fuse to trip and interrupt the current flow. Bonding ensures that all metal parts of an electrical system or equipment are at the same potential, reducing the risk of electric shock. The NEC provides specific requirements for grounding and bonding in various types of electrical systems, including residential, commercial, and industrial systems. These requirements cover topics such as the size and type of grounding conductors, the location and type of grounding electrodes, and the methods for bonding metal parts of an electrical system or equipment together. The NEC also provides requirements for the grounding and bonding of specific types of equipment, such as motors, generators, and transformers. These requirements are designed to ensure that these equipment are properly grounded and bonded to prevent electric shock and other electrical hazards. In addition to the NEC, there may also be local codes and regulations that apply to grounding and bonding. It is important to consult with a qualified electrician to ensure that your electrical system is in compliance with all applicable codes and regulations. Proper grounding and bonding are essential for the safety of people and property. By following the requirements of the NEC and other applicable codes and regulations, you can help to prevent electric shock, fire, and other electrical hazards. The Home Inspector's recommendation to contact a licensed electrician is a prudent one. A qualified electrician will have the knowledge and experience to evaluate the electrical grounding system, identify any problems, and recommend appropriate solutions. The electrician will also be able to ensure that the electrical system is in compliance with all applicable codes and regulations. When selecting an electrician, it is important to choose one who is licensed and insured. A licensed electrician has met the requirements of the state or local licensing board and has demonstrated competence in electrical work. An insured electrician has liability insurance to protect you in case of any accidents or damages that may occur during the electrical work. It is also a good idea to ask the electrician for references from previous customers. This will allow you to check on the quality of their work and their customer service. Once you have selected an electrician, be sure to get a written estimate for the work to be performed. The estimate should include a detailed description of the work, the materials to be used, and the total cost. It is also important to discuss the payment terms with the electrician before the work begins. By taking these steps, you can help to ensure that you are getting quality electrical work at a fair price. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factor. People should be aware of the risks of electricity and should take precautions to avoid electric shock. Some simple precautions that can be taken include avoiding contact with exposed electrical wires, using properly grounded tools and appliances, and staying away from electrical equipment during thunderstorms. It is also important to teach children about the dangers of electricity and to keep them away from electrical hazards. By educating people about the risks of electricity and by taking precautions to avoid electric shock, we can help to create a safer environment for everyone. Also, consider the age of the home, which was built in 1993. Electrical codes and best practices evolve over time. What was considered acceptable in 1993 may not meet current standards. An electrician can assess whether the existing grounding system meets modern requirements and recommend upgrades if necessary. While gas water heaters are present, it is crucial to understand that grounding is primarily related to the electrical system, not the gas system. However, proper bonding of metal gas pipes is still important to minimize the risk of electrical shock in case of a fault. The electrician will inspect the bonding of the gas pipes as part of the overall assessment. The mention of a ground from the main breaker box to a lightning ground is somewhat unclear. A lightning protection system is separate from the electrical grounding system and should not be directly connected. The electrician will need to investigate this connection to ensure it is safe and code compliant. Step potential is more likely to occur in areas with high ground fault current, such as near electrical substations or industrial facilities. However, it can still occur in residential settings if there is a fault in the grounding system. The electrician will assess the potential for step potential based on the specific characteristics of the electrical system and the surrounding environment. Finally, while GFCIs are recommended for additional protection, they are not a substitute for a properly installed and maintained grounding system. GFCIs protect against ground faults, but they do not prevent step potential. A comprehensive approach that includes both proper grounding and GFCIs provides the best protection against electrical hazards.